Acids and bases. I would caution you to go back and figure out where you went wrong with the equilibrium problems, because acids and bases are at least half discussion is equilibrium. You got to know how to write the equilibrium expression and then use it to solve the problem. I saw some of your equilibrium expressions were missing powers and were flipped reactants and products the wrong way. Practice is the only thing that's going to fix that. All right, acids and bases. From a historical perspective, the first, I guess you would call it, scientific approach to try to describe what an acid and a base was came from Arrhenius. We've heard from Arrhenius before in kinetics, but he did lots of different things. And his definition of an acid was any molecule, and this could be anything. What you have is, from our nomenclature, right? Acids have to have this hydrogen out in front, 1, 2, or 3 of them. I'm just using an example where we only have one. And he said, in aqueous solution, that would dissociate into a proton and what was left over. That was his definition of an acid. He defined base as any molecule that had a hydroxyl in it. And in an aqueous solution, it would dissociate into those. So this produced the acid effect, which would be sour. Right? It had a sour taste. Base would be a bitter taste. Right? If we still tasted our chemicals, but we don't do that anymore. But when you taste, when you know what an acid tastes like, when you taste acid like swallow vinegar, you know it's due to that hydrogen. And when you chunk down on a pill, a medicine, and it tastes bitter, that's because it's basic. A lot of them are. This had a very limited application, but it was a start. The problem came when we recognized bases, but the molecule didn't have a hydroxyl in it. The best example of that is ammonia. When you put ammonia in solution, right, just add water, you get hydroxyls. Where'd they come from? Right? So subsequently and independently, Lowry and Bronsted, I think Bronsted was Danish, Lowry was English. They came up at the same time. They proposed an alternate definition for acids and bases. The acids could be like that, only now the acid would serve as a reactant with water, and the proton would be transferred to the water. So that means we would have this new polyatomic ion called the hydronium. And what was left over was this part of the molecule. Okay, so that's a little bit different than Arrhenius' definition. So for Bronsted and Lowry, an acid is any compound that can donate a proton. So acids donate. And we don't even consider the hydroxyl in Bronsted and Lowry's definition. In their definition, bases accepts a proton. So here's what happens with this one. The proton now is transferred from water. And you end up with an ammonium polyatomic ion, and there's your hydroxyl. So Bronsted and Lowry's definition is broader. It encompasses more territory. It's still aqueous solution, though. We're still in aqueous solution with Bronsted and Lowry. Okay. So let me clear the field. When we talk about an acid and a base, we're going to use here hydrochloric acid. All right, that's aqueous solution. What would it be if it weren't an aqueous solution? If it were a gas? Hydrogen chloride, right? When you put it in water, then you give it the acid name. All right. And by Bronsted and Lowry's definition, and what we've learned so far about equilibrium, it can go forwards and backwards. This is the acid, and water becomes the base. And when it transfers a proton over here to water, we have the chloride left over. This is the pure liquid. And we have the hydronium ion. Okay. I think there's a slide coming up, but since stream of consciousness, if this is an acid and it produces this molecule, what can this molecule do according to Bronsted and Lowry? It can accept a proton, can it? Okay, so that makes it a base. Only to differentiate this from that, we call this the conjugate base of that acid. And by the same reasoning, this base leads to this acid. This is the conjugate acid of that base. The reason we're building this vocabulary is because if you know the behavior of this acid, right, strong, weak, whatever, then you can predict the behavior of its conjugate base. All right. Okay. I think this is just an idea of where you have the ammonia molecule in blue and water molecule in red is playing tug of war with that hydrogen. I will say this also. When you have this possibility where you have that molecule, this is a covalent bond. Okay? So when it loses that proton, when it donates that proton, we say that it's being ionized. I mean, it's yes, it's ionized. Because it's not an ion yet. It's only an ion when it transfers that and leaves the chloride behind. If we have a base in which there's a hydroxyl, let's use something real, sodium hydroxide. Sodium hydroxide. When it dissociates in water, that's exactly what we call it. This is an ionic compound. That's a covalent compound. So this ionic simply has to dissociate into aqueous solution. Okay. Terminology. Sometimes I get them mixed up, so if I do, and you want to, you can correct me. So the bottom example there, you have two water molecules, I think. Yeah, two water molecules. So what do? Water molecule, well, there's our acid base and conjugates. Yeah, while we're on that topic, if you have a water molecule in here, and it's pure water, nothing else is in there, you can still get a reaction between these two water molecules, right? Maybe this proton right here goes to that one. So what does that leave us? That leaves us a hydroxyl over here and a hydronium over here. Water can do that. Ammonia, pure ammonia can do that too. That's a different reaction, but it can self-ionize. We're going to talk about that a little more in a minute. Okay, so there are definitions. Acid base, conjugate acid, conjugate base. Now I want to give you the chemical definition of a strong acid and a weak acid. A strong acid is one that when you put it in water, it ionizes completely. Like hydrogen chloride going into solution. It produces only hydrogen ions, well, attached to, right, a water molecule, and chloride ions. That's a strong acid by chemical definition. Now, will it do damage? Only if it's concentrated enough. And if you have, say, I don't know, 5 molar hydrochloric acid, or you have concentrated hydrochloric acid, which in most cases is 37%. You can get it stronger, but we typically only use 37%. That will cause damage. But if you have like a 10th molar, that's like stomach acid. I mean, it'll still damage your skin, but it won't happen very quick. Okay. So the popular definition of strong and weak is not the same as the chemical definition. Chemical definition looks at the individual molecule. What does it do? Does it ionize completely? Yeah, it's a strong acid. A weak acid is one that doesn't ionize completely, like vinegar. Right? C2H3O2. So there's your acidic hydrogen. And that can be transferred to a water molecule, right, and give you your hydronium. What do you have left over? You have your acetate polyatomic ion. This one prefers, that should be plus, well, plus, but the proton is transferred. This one prefers that form. It does not ionize very much. It's a weak acid. That's the definition of a weak acid. Now, I mentioned that conjugates, acids and conjugate bases could be characterized based upon their acids and bases that they come from. If you have a strong acid like this, right, and it produces the hydronium ion plus the chloride ion. So there's your conjugate base. And there's your strong acid. If you have a strong acid, it produces a weak conjugate base. Now, the definition is, of course, what we talked about here. Strong acid ionizes completely. Right? So if it ionizes completely, that means the hydrogen can leave that molecule very easily. That means that there's not much motivation for any hydrogens to rejoin the chloride. That's what we're saying. If this is strong and it wants to get rid of the hydrogen, then its conjugate base doesn't want the hydrogen back. So strong leads to weak. Okay. And by the same logic, weak leads to strong conjugate base for a weak acid. That acetate ion wants protons, and it'll take them from anybody it'll give them. If it's got, if you've got hydroniums in there in that solution, it'll grab onto that and go backwards. If you put this in aqueous solution, right? Say, how would you get that in aqueous solution without the hydrogen attached to it? It's got to have a counter ion, right? Everything is neutral in chemistry. Why don't we just say, all right, pair it up with a sodium. Okay. Sodium acetate, throw that in water. And what would happen? Well, the sodium is not going to react with anything. It's a spectator. But this ion, once you get it in solution, right, It sees water molecules and it's a strong base. So it's going to take a proton. This now becomes the acid and this is the base. Right? So we transfer a proton over here. That gives you the acetic acid here. And what's left over? Right? We took a proton from it. So OH minus is all that's left. Okay. So that's the behavior of conjugate acids and conjugate bases. Oh, you're right.
Okay.
Okay. All right. This is just your the author of your book's idea of explaining strong acids and weak acids. The one on the left is a strong acid because it produces high C2H3O2 in aqueous solution. We would write it this way for convenience. But we know that's not what happens. What happens is it reacts with water and produces a hydronium. But the calculations are all exactly the same. They give you the same results, whether you use the correct chemical formula, a reaction, or you use the abbreviated form. So in this picture, we see hydrogen ions and the anion that's left over for a strong acid. For a weak acid, HB, that's a bad choice because B means base to me. HB leads to mostly still HB. A little bit of hydrogen ions and a little bit of B minus. That's a weak acid. Okay. Now, if we say use this format, and this is in equilibrium, right? We know it prefers to be over here, but we can express that quantitatively because we know how to write an equilibrium expression. So what's the K for this expression? Right? It'll be the hydrogen ions or the hydroniums, whichever you prefer. C2H3O2 minus, because that's a product, and then this part of the molecule, this part of the expression. There we go. That's the equilibrium expression for acetic acid in aqueous solution. And we give it a subscript of A to represent the acid dissociation or acid ionization constant. Okay. So if this is very large, now it won't be for acetic acid, but if it were, if the Ka were very large, that means you have lots of product and very little reactant left. That's a strong acid or stronger acid. If this is very small, that means you have very little of this and you have mostly that. That's a very weak acid. And they run the range, right? I'm trying to remember. The Ka for acetic acid, I think, is 1.8 times 10 to the minus 5. When we do the Ka next week, we're going to determine the Ka for acetic acid experimentally.
You said if the K is large, then we have lots of products.
Yes.
Okay.
Yes. That's not necessarily a strong acid, but a stronger acid. And the equilibrium lies far to the right. Okay. That's what that table 14.1 is summarizing. Okay, here's what I was talking about earlier, where water reacts with itself. That sometimes we call it self-ionization, auto-ionization. And I mentioned ammonia can do it too. And the bottom reaction is one where pure ammonia, we call it anhydrous ammonia, means there's no water. And a proton is transferred from one to the other. Farmers use this. Farmers that have a lot of, say, corn, they need lots of nitrogen. Corn is a nitrogen sponge. All grasses are. But if you have the equipment and you have a source of anhydrous ammonia, it can be cheaper to deliver the nitrogen to your crop using that equipment than it can with other solid fertilizers like ammonium nitrate or urea, those types. But you have to have, everything has to be stainless steel. If it's not, ammonia will eat it up. So all their equipment is stainless steel. They have this big stainless steel tank being pulled behind the tractor, and then it's delivering liquids, pumping the anhydrous ammonia into the injectors. These stainless steel knives that go down under the soil into the moisture part of the soil and injects that ammonia in there. If you don't do that, if you just try to blow it on the ground, it'll just evaporate. It's gone. So you inject it in the ground and it reacts with the water and produces an extremely basic environment, which is basic enough to kill everything. So you don't want to put it, if you've already got a crop growing, you want to put it in the middle, not on your crop. And it kills all the microorganisms, it kills everything, roots, weeds, whatever. And then gradually, the microbes and the roots reinvade as it dissipates. By the time it gets to your plant, it's not dangerous, but it does provide them with nitrogen. But in that tank, this reaction is going on. You get ammonium ion, and then you get the amine anion, NH2. So sometimes we call this an amphoteric behavior. Ampho meaning both. That's Greek. Prefix means both. So that means the molecule can act as an acid and a base. Now, water at 25 degrees, actually it's 24 degrees. I'm not going to haggle over a degree. When you dissociate water, right, and we're going to use this as the abbreviated form, right, in equilibrium with that and that. It's more convenient to do it that way. The K for this expression is what? This is a pure liquid. These are in aqueous solution. So remember what we said about pure liquids and solids? You don't put them in the expression, right? So this one is only that and that. Okay. And this is given KW. Water has its own K subscript. W belongs to nobody else but water. And at actually 24 degrees, the value is 1 times 10 to the minus 14. It's extremely small. That means that even in pure water, it's mostly there. It's just tiny amounts of this. Okay. Now, one other fact that you need to keep in the back of your mind is no matter what we do in aqueous solution, say we put a weak acid into aqueous solution, this is still happening, right? The acid we put in there is doing its thing, but water's still doing its thing. So they both happen at the same time. What we have to decide when we start to solve problems is which one is dominant. You can put acids in water that are so weak that they don't make, they have no effect. Because their Ks are less than that. This K is bigger, so the dissociation of water is what dominates. But if the K of your acid is bigger than that, then, especially if it's an order of magnitude or more, then we can ignore this one. All right. Let's see. 3 possible situations. Now that we're talking about water, what situation is it where this one is equal to that one? If these two are exactly equal, then there's no imbalance. You don't have excess hydrogen ions, you don't have excess hydroxyls. So it's not acid and it's not basic. And we call that neutral. So if these are 2 equals, then we have neutral. Oops, too many L's. So what does that mean for the actual concentration? If they're equal, and this is the value that you get from K, they have to be 10 to the minus 7, right? 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. You just add the powers, right? Right, that's a math problem. Now, if we increase the temperature, we're going to get more dissociation. But if it's just pure water, it's still going to produce equal amounts here. And that will change. Remember, K's change with temperature. So this value is only valid at 24 or 25, close enough. But the neutral solution is equal concentrations. And at 25 degrees, it's 10 to the minus 7. Now, in an acidic situation, you're going to have more hydrogen. Right? Hydrogen ion concentration is greater than hydroxyls. Okay, that's acidic. So what are the possibilities? Well, we could just pull something out of the air. Say we increase this one to say 10 to the minus 6. What would hydroxyl have to be? That's a constant, right? So if this is 10 to the minus 6, what does that one have to be? 10 to the minus 8, right? Add them together, 10 to the minus 14, right? That's a constant, right? So if this one is that value, this one has to be that value. And that happens even if we add an acid to it. Right? If we add an acid to bring this concentration of hydrogen ion up, then this one has to go down because we cannot defy that constant. That equilibrium must be honored. Basic, right? Base, say we went the other direction. Say instead we added a base, and now the hydroxyl ion concentration is 10 to the minus 6. Now, and this is all in molarity, of course. Now this one is 10 to the minus 7. That's a basic solution where hydrogen ion concentration at equilibrium is less than hydroxyls. Okay. All right. Next. All right, we discussed this already. Acid base, conjugate acid, conjugate base. What's the equilibrium constant expression for an acid acting in water? Well, that is the true chemical activity, the equation for an acid dissolved in water. So if we wrote the K for that one, this is a generic K. So we would have hydronium ions and the conjugate base divided by the acid. And water's a pure liquid, it's not there. Don't put it in the expression. Why? Because water doesn't change its concentration. Okay, that's a generalized expression. If I got it right. Yeah, okay. Okay, so just the reality check. If the equilibrium lies to the right, the value of Ka is what? Large. Greater than. We can't say that. Okay, this is the same thing for acids and base equilibrium as it is for all other types of equilibrium. We can't actually say that the K value for any equilibrium, if it's equal to 1, then you have equal amounts on either side because you've got the stoichiometry to deal with. But we can say if that value is extremely large, much greater than 1, then we can say the equilibrium lies to the right. For acids and bases, for any equilibrium. And then, of course, if the equilibrium lies to the left, we're going to have a small value of K. Let's see. For this same expression, it's not up here, it's on the board, on the screen. If water is a better base than A minus, what does that mean? When we talk about a base is a proton acceptor, a hydrogen ion acceptor. So if water is a better hydrogen ion acceptor than A minus, that means it wants protons more than A minus does. So if that's the case, then which side is the equilibrium going to lie? No, if it wants a proton, if it's a stronger base, it's right, it's going to accept a proton anywhere it can get it. So the equilibrium is going to be on the right. Right? If water's a stronger base than A minus. Let's see. Did I fill that in? Yeah, products are dominant. Does this mean that HA is a strong or a weak acid? By comparison, if A minus is weaker than water, HA must be a weak acid. Excuse me, a strong acid. Yeah, a strong acid because it produces a weaker A minus. Yeah. Yeah, it's a strong acid. How about the value of Ka? Greater or less than 1? Well, if it lies to the right, it has to be greater than 1, doesn't it? All right. So let's make room. Let's see. Doing on time. Okay. Order these from strongest to weakest base. We've got water. Need the marker. Water. We've got A minus. And this is from a weak acid. From a weak acid. Okay. And we have chloride. Right? So I would look at these first. All right, if we want to order from strongest to weakest base. This base comes from a strong acid, so it's very, very weak. So it would be the weakest. And the strongest would be this one. From a weak acid, this is a very strong base. That puts water in the middle. That was fairly easy. Okay. Okay. All right, consider, we looked at this one before. I sort of jumped the gun, I think. Where we had acetate ion, we put it in solution without the hydrogen ion attached. We put the strong conjugate base, the acetate ion, in water. And what did it do? It took a proton from water and left you with the conjugate base of water. So which way will the equilibrium lie? Think about it this way. The conjugate acid of that base, A minus, if A minus is strong, HA has to be weak. In other words, it wants to be there as HA. It doesn't want to dissociate and go backwards. So we're saying that it lies to the right. The reason I did that was that the slide that was created by the publishers must have been done by contract labor because they put the wrong answer in there. So it came up left first. I X'd it out and said it lies to the right. Okay, how about this one? Solution where A minus is the anion of a weak acid HA. Is the value of Kb greater than or less than 1? All right, we haven't written Kb yet, but if we did, we'd write it exactly the same way. We'd have HA, right, at equilibrium, HA, right, products, like that, products in the numerator, right? Water's a liquid, so this goes in the denominator. That would be the Kb for that reaction. Okay. So in this case, if it lies to the right, Kb should be large, shouldn't it? Should be greater than 1. I had to do it again. I got it wrong the first time. Okay. Let's see. Does this mean that A minus is a strong or a weak base? Well, it's a strong base, right? It's going to latch on to hydrogen ions wherever it can find them. Here we go again. All right. So acetic acid and hydrocyanic acid are both weak. Acetic acid is stronger than hydrocyanic acid. So arrange these bases from weakest to strongest and explain. So if we've got this weak acid, C2H3O2, then it's going to be in equilibrium with that plus this. Okay. And hydrocyanic, I'm leaving out the aqueous part just for convenience. The hydrocyanic acid, of course, is in aqueous solution, and when it ionizes, it produces that. Okay. Now, the K expression for each one, might as well write it, be thorough. The K for this one, of course, is hydrogen ions, acetate ions, divided by the unionized acetic acid. Okay, this Ka is going to be hydrogen ions again, the cyanide ion, and the hydrocyanic acid. There we go. Now, if we're saying that this one is stronger than that one, that means this Ka, let's see, this Ka, I think it's called 1, 2. This Ka is larger than that Ka. Right, so Ka1 is greater than Ka2. We want to order these in the order of strength. So if this is a stronger acid, what does that say about their bases? That means this one is stronger than this one. If that's a stronger acid, it's a weaker base. So that's the order for those two. Okay. Now we've got chloride in there. that's going to be the weakest base. They want it order weakest to strongest. So we're going to put chloride here first. That's the weakest. How about the strongest? The strongest is probably that one. Okay. Now what we have to do is say, all right, where does water and acetate ion come in? Well, this acetate, if you put that in solution, it's going to make by itself. Put it in water, it's going to make a basic solution. So it's probably more basic than water is. It wants hydrogen ions worse than water does. So that's why I would put it here. And then water here. As far as strength of base is. Now, the nice thing about this explanation is it actually gives you values. So this Ka over here is equal to 6.2 times 10 to the minus 10. And this one is 1, yeah, I guess right, 1.8 times 10 to the minus 5. And then water is, the Kw for water is 1 times 10 to the minus 14. Okay, so let's see. You know what that means? Oh no, I'm sorry. We're talking about water, not OH minus. Right, the conjugate base of water is the hydroxyl, but that's not in there. So we're talking about water. How bad does water want that proton? That's what this one means. So I think I've got them in the right order. Yeah, chloride, water, acetate, and cyanide. All right. Now, suppose we're reacting an acid with a base, not with water anymore. We could just dump them together, right? Or we could do it in increments. We call that a titration. Did we do a titration in the first semester? Yeah. Does that bring back memories? No. It's been a while, I guess. Where you have let's see, what we had. We had an acid in the beaker and we added base, right? So we put an indicator in there that would change color when it went from acid to base. The phenolphthalein would be clear. And then we started adding base. And initially it would go in and mixing around. You'd see a little pink spot disappear. And it gets stronger and stronger as you reach the end point. We're going to do something like that next week. We're going to titrate acetic acid with sodium hydroxide and draw a titration curve to find out what the Ka is. And that's explained in nauseating detail in the procedure. Okay, let me get back to this one. Discuss whether the value of K for this reaction is greater than 1, less than 1, or equal to 1. All right, let's see. Do they give us an explanation, a way to work it out? Yeah, they start working it out here. Okay, so let me put the equation up here. We're reacting this acid in aqueous solution and this base. And the potential reaction is HF plus Cn minus. And this is all aqueous solution. And I got those backwards. Okay, we're also given Ka for this one, Ka equals 6.2 times 10 to the minus 10. This is a K for HCN. And the Ka for HF, they give it to us as 7.2 times 10 to the minus 4. 4. All right. What we need to do is decide which side is favored. If this acid is very, very weak, then it's going to produce a strong conjugate base. This one is weak, but it's not as weak. In fact, it's 6 orders of magnitude stronger. So this one is stronger. It's driving that way. This one's driving that way, but this one is a stronger acid. The drive is more toward this side. Okay, you can look at it that way. Compare the Kas for the acids. And which one wins as an acid? This one does. Or you can say this one is a weaker acid. It produces a stronger base than this one does. So that in itself drives this way also. So either way tells us that the equilibrium lies to the left. That means that we have less product, more reactant, and the K is less than 1. Let's see. All right, what does each one mean? Right. Let's see. Ka for HCN is much less than Ka for HF, right? HCN driving reaction toward HCN, yes. That is to the left. So our Ka, that's a different explanation, but I think I like the way I said it first. Makes more sense. When you're in competition, if we're doing just a qualitative assessment, a semi-quantitative, right? Because we do have values. Then that's a good explanation. We're going to learn how to calculate what the K is for that reaction. All right. Calculate KB when you know Ka. All right. So let's say, are they going to use a example? No, they're using generic. So let's go through the generic slide and then we'll use an example. I'll leave those on the board so we can use one of them. So the Ka expression for this acid, HA, is A minus times hydrogen ions divided by HA. What would be the Kb? The Kb for that reaction would take the conjugate base and put it in water without the hydrogens. I have some kind of counter ion, potassium, sodium, lithium, usually because those are all soluble. Then what would be the expression for that one? There's the expression, right? The acid times the hydroxyl divided by the anion. Right. So notice that the Ka and the Kb are different forms. You can't just take the Ka and do the inverse. It doesn't work that way. Okay. So what happens if we add those two together? We add those two equations together. Right. The HAs cancel. The A minuses cancel. What are you left with? You're left with dissociating water, which is what? There it is. That box is supposed to be a time sign. So when you multiply, and remember, when you combine, the equilibrium constants then are multiplied by one another. Remember that? Okay. So when you add the equations, you multiply the Ks. So the Ka times the Kb is equal to Kw, which is hydrogen ions times hydroxyl ions.
When we do this, is it math where we put H, no H at the end? Like, is that placement?
That's just, okay. That's just explaining why Ka times Kb equals Kw. You don't have to put the hydrogen ions and the hydroxyls in there. What we're after is this one. Ka times Kb equals Kw. That's the equation we're at. So if you know Ka, solve for Ka is Kw divided by Kb. Actually. No. We're trying to find Kb, huh? Kb then is equal to Kw divided by Ka. Right? Which is 1 times 10 to the minus 14 divided by Ka. So you just divide Ka into 10 to the minus 14 and you get Kb for the conjugate base. There you go. Yeah, that's put in there just to prove the point. Okay. Or if you know Kb, you can just swap these and you get the same thing. Sometimes you will need Kb, not Ka. Okay, what's the value of K for this reaction? Let's see. Yeah, that's the one we had on the board. Come on. There we go. If we break this reaction into two competing dissociations, right? There's the hydrocyanic acid in its dissociation. There's the HF in its dissociation. But what's wrong with that equation? It's backwards. So there's the expression for hydrocyanic acid. There's the expression for HF, but we need the inverse of that one. So in this case, we do invert the equation. And when you invert the equation, you just take the reciprocal of 7.2 times 10 to the minus 4. Right? Yeah. So there it is, 1.4 times 10 to the third. Then when you add those two equations together on the next page, like that, add those two together, then you get that equation right there. And now you multiply those two KFs together. The unmodified hydrocyanic acid K, and then the inverted HF. And that'll give us the K for the reaction, which is 10 to the minus 7. And that verifies what we assumed before. It's less than 1, it's far to the left. All right. That's a quantitative justification. All right, let's talk about pH. Everybody's heard about pH, right? You've heard of pH? Yeah, okay. Go back to basics. pH is a mathematical transformation. Let's see, do I give any history? Ooh, no, I need to give you some history. There was I think he was Swedish, a guy by the name of Sorensen. Okay, he was working, and his graduate students were working with proteins and how they behaved at different acid levels. Right? You increase the acid level, you get a different response in your proteins. But they were very minor changes, right? There's small changes. And if you use the concentration of hydrogen ions as one of your parameters, and you'd have to express that in scientific notation, right? Like a number like that. He wanted something a little more convenient. So he said, okay, here's what we're going to do. We're going to take that number, that hydrogen ion concentration, and we're going to do a log transform on it. Common log, base 10. Right? But what does that do? If this is 10 to say minus 7 here, what is the log of that number? It's the power of 10 that is this number. So the power of 10 that is that number is minus 7, isn't it? So that would be minus 7 in this case right here. But you didn't want minuses either, right? They're a distraction. So I said, okay, my mathematical transformation is just going to do that. So the log of hydrogen ion concentrations at this level is 7. And you can do that, and he called it pH. This references the hydrogen ion concentration. And P, I can't remember what P stood for, but it's always small p, big H. Right? If you write it like this, right, that's phosphorus and hydrogen. If you write it like this, that's phenyl group in organic chemistry. Right? If it's not written that way, it's not pH. Okay. So once this transformation was made, he and his students were able to use numbers that were more manageable. One thing I will say is when you do this log transformation, you trying to track your significant figures can be a problem unless you remember this rule. If we have significant figures of hydrogen ions, let's pick a number. Hydrogen ions, say it's 3.75 times 10 to the minus 5. Okay. I'll need my calculator for this one. I'm going to do the pH of that. So the negative log of that value will give me what? 3.75. Get my exponent in here and take the log of it and then change the sign. So I get, my calculator tells me it's 4.4260. So how many decimal places can you have in the log? The number of decimal places in the log is equal to the number of significant figures in your original value. So we have 3 significant figures, right? The decimal places in your log can be 3. So all we have to do is get rid of this last one. Right there. And that's the proper pH with correct significant figures. The number of significant figures here equals the number of decimals here. And if you go backwards, the number of decimals here equals the number of significant figures there. So how would I go backwards? Right. If we said the negative log of hydrogen ions was equal to 4.426, how would I get that value right there? Okay. We need to get rid of that negative first. So we go back here like that. Negative 4.426. Now we go to our definition. Base 10. 10 to that power is this number. That's what logs mean. So if you put in your calculator minus 4.426 and make it the power of 10, you'll get that number. Okay, you can check me out to see if I'm right. That's called the anti-log. 10 to the x. Is there a key in there for 10 to the x? Okay, that's your anti-log. Some calculators actually say anti-log, but I like 10 to the x better. It's more mathematical. Okay. So far, so good. Questions? Let's see if
Because my calculator's like crazy.
you're supposed to get 3.75 times 10 to the minus 5.
Mine's like 0.000037.
Do the
Yeah.
anti,
You don't have it in scientific notation. It's not spitting the values out in scientific notation. Yeah, that's right though. And since this has 3 decimal places, your coefficient has 3 significant figures. That's just the way logs work. We don't have time to go into the details. So just accept it. Right? Right. I'm glad you agree. All right, I'll do it on time. We're coming up on 11, and we're good till
1:30.
11:15, then a break, and 11:30 we'll have a lab. Okay. All right, so if we do the pH, we know that what's the hydrogen ion concentration in a neutral solution at 25 degrees Celsius? That's equal to 1 times 10 to the minus 7 molar, isn't it? Right? Neutral. Why? Because Kw equals this times that equals 1 times 10 to the minus 14. And if that number is going to be 10 to the minus 14, the only way you can get there in a neutral solution is 10 to the minus 7, 10 to the minus 7. Okay? So I did that one earlier. The negative log of 10 to the minus 7 is equal to 7. Actually, 1 decimal place. That's pH. So that's neutral pH at 25 degrees. pH 7. If the value is bigger than that, say it's 10 to the minus 6, what's the negative log of that? That's 6. So as you become more acid, as the hydrogen ion concentration increases, the pH decreases. So the lower the pH, the more acidic, and the higher the pH, the more basic. All right. And there's some examples. We don't need to go through all of them. Pure water's in the middle. It's kind of small to read too. It's 7. Milk is a little bit slightly acidic. Blood is slightly basic. Anybody had anatomy and physiology? Okay. What's the pH of your blood when you're healthy? I'll start it off. 7 point. Huh? About 4. Yeah. It's 7.35 to 7.45. Very, very narrow range. If you're outside that range, you're going to feel bad. So the blood is, we're going to talk about this in the next chapter. The blood is strongly buffered for that pH range. And I'll have to describe what I mean by that later. Other things like stomach acid. Normally your stomach acid is about pH 2. You know, unless you eat a big meal full of tomatoes, and then it probably dropped to 1. Let's see, what are some other things? Baking soda in water, 8.5. Ammonia, that household ammonia cleaner is 12. The OSHA, I can't remember, I think it's OSHA, defines a caustic solution, caustic material, pH less than 1.5 and greater than 12, or greater than 12. Either way is considered hazardous for your working environment, and you have to dress accordingly. Which means that when we go in that lab, we're using concentrated ammonia, and we're using concentrated hydrochloric acid and concentrated nitric acid. So we need to dress accordingly, protect ourselves. Because when you get that strength of acid and base, it goes off the pH scale. You can still do the calculation because this is nothing but math. But your acids could be negative, right? If you have a 1 molar solution of acid, right, what's the negative log of that? Right? Well, let's see. We're going to have 10 to the first power, right? 10 to actually, the value is 1, right? 1. pH is -1. If your concentration is 1 molar. Actually, this is 10 molar. 10 molar. Okay, all right. So let's see what else we can get done before I run out of time. Calculate the pH of the following solution. First one's easy, right? Because it's the coefficient is 1. All right, let's review. If we have the log, negative log of 1 times 10 to the minus 4 hydrogen ions, if you take the log of a product, what do you do with that number? It's the same thing as saying negative log of 1 plus minus log of 10 to the minus 4. Right? That's what logs mean. Right? If you've got a product in here, then you take the log of this one and add it to the log of that one. Remember that from math? Nobody remembers that. Okay. Well, what I'm trying to say is these are both base 10, right? So what number, what power of 10 gives you 1? Big 0. Right? So this one is 0. That's why when I did the earlier negative logs of those, like 1 times 10 to the minus 14, I just ignored the 1 because it's equal to 0. You add that to this one, and this one is 4, right? pH 4. There we go. Ooh, okay. Suppose you're not given the hydrogen ion concentration, but instead you're given the hydroxyl ion concentration. So 0.040 molar equals the hydroxide ion concentration. We can't calculate pH until we know the hydrogen ion concentration, right? So how about this? Remember, it's always happening, isn't it? Like that? This is KW. That's always happening. Okay, so let's substitute 0.040 right here and solve for that. So that means the hydrogen ion concentration is 1 times 10 to the minus 14 divided by, let's see, 4 times 10 to the minus 2. Okay. So we can do some of that in our heads, right? 1/4 is 0.25, right? And then what's 10 to the minus 14 divided by 10 to the minus 2? You just take this one and subtract it from that one. So you subtract the negative, it's a positive 12. There we go. So we got 2.5 times 10 to the minus 13. That's the hydrogen ion concentration. Now we just take the negative log of it. Okay. Nobody's going to do that.
And that's when you do the inverse log, right? To get the negative.
Well, you take the log of this and then change the sign.
Okay.
Just punch in 2.5 and then your exponent as minus 13. Take the log of it. It's minus 12.6. And the minus sign makes it 12.6 pH. Okay. That's the long way to do it. I'm going to show you a shortcut in a minute.
When I put that in, it's saying error. I guess I'm putting in.
2.5 times 10 to the minus 13. Then take the log of it.
Yeah.
Or do you have to say log first?
Log first.
Yeah.
That's possible.
And then put it in. You're trying to do reverse Polish notation on an algebraic calculator. It works on this one. This is RPN.
I thought that's why I get something
Okay.
confused.
Yeah, I got it now.
Okay. You're confused because of the way your calculator will and will not accept information.
But yeah, because you say it that one way, so I think that's how we have to enter it, and then
Oh,
we can't
no.
enter it
That's
that way.
That's how my
Yeah.
brain works.
So I'm gonna need you
You have
to.
to translate it to your universe.
I need you to translate it to my universe.
If you're using algebraic calculator, you put your information in one way. It usually requires parentheses.
Now I'm getting a negative, so we just drop the negative.
Yes, the
That's a
negative
negative
times that
log.
value.
Okay.
Yeah. Mhm. Now, in my universe, RPN, I say 1, enter, 1 plus gives me the answer. Or I put in that number and I go up here and hit log. It gives me the negative number, and then I just change the sign. Now, I don't have to use parentheses, not in my calculator. They don't make, Texas Instrument came out with this form. It was a TF, it was a 42. And they stopped making them. And that was the best calculator they ever made. Now this company, Swiss Micros, is taking that same form and they're building it for us. It's not cheap, but it's the best calculator ever made. For my work anyway. It won't graph. But once you get familiar with and get comfortable with reverse Polish notation, you won't go back to algebraic. It's so much faster and easier. Okay, enough of that. pH of a solution is 5.85. What's the hydrogen ion concentration for this one? That's where you set it up like negative log of hydrogen ion concentration is equal to 5.85. Okay, so we got to get rid of that negative sign. You can't have a negative here and do the calculation. So we say move the negative to the other side. Negative 5.85. Now the concentration of hydrogen ions is equal to 10 to the minus 5.85. It's a whole lot easier now than it used to be. Before we had calculators, we had to go to tables, log tables, and figure out what that was out of the log table. It was a nightmare. I love calculators for that. Okay, so if we do that calculation, there you go, we get hydrogen ion concentration of 1.4 times 10 to the minus 6 molar. Okay. All right. Now, we're going to give you the shortened version. Remember I said Sorensen's log transformation is simply math, which means you can do that math conversion to any concentration. Right? If we do it to hydrogen ions, right, we get pH. What if we did it to hydroxyl ions? What would we call that? POH. Okay. And while we're here, what if we have a Ka? That becomes pKa. Okay. It's just math. But we're going to be able to use it to simplify our problem. Okay. The other one, if this is Kw for water, that's pKw. This one is 10 to the minus 14. So what's pKw equal to? 14. 10 to the minus 14 power is that value. Take the negative of it, you get 14. Okay, that's what we're trying to do here. In this case, we set it up as Kw equals hydrogen ions times hydroxyl ions equals 10 to the minus 14. We're going to take the negative log of that entire expression. Negative log of Kw, negative log of hydrogen ions, negative log of hydroxyls, right? And when you take the log, you have to add them together. But there's a negative sign in there, so we have to put that in. So what does each one of those mean? Well, each one means pKw equals pH plus POH. pKw equals pH plus POH, which means 14 equals pH plus POH. So if you're given hydroxyl ions and you ask what's the hydrogen ion concentration, or you're asked what the pH is, let's say you're given hydroxyls, just calculate the POH, subtract it from 14, and that's your pH. That's a lot easier than going the other route. Let's see. Okay, here's an example. Calculate the POH for this one. Well, we're going to calculate the pH for that one will be 4, right? So 4 would be here. 4 subtracted from 14 is 10. So POH is 10. Right? And if we want POH from the other one, well, let's see. We just do the transformation, 1.4. If we have a pH of 5.85, what's the hydroxyl ion concentration? Well, find out what POH is. 5.85 subtracted from 14. Let's see, do I have that worked out? No, I don't. Subtract 5.85 from 14.
8.1. That's
8.15. Yeah,
that's what I got.
this is the POH. And the OH concentration is equal to 10 to the minus 8.15. Which should be this value. 7.1 times 10 to the minus 9. Okay? That's the quick way to do it.
Where's the 7.1 come from though?
From your calculator.
Oh,
If
well, okay then.
you put in 8.15, let me change the sign, and then I do the 10 to the x, that gives me 7.0795 times 10 to the minus 9. And since we have 2 decimal places, the answer can have 2 significant figures in the coefficient. That's why 7.1 is all you can do out of that.
So
Not working?
so
I want it again, so again.
How do we do it again?
Yeah, like the 7.4.
I get 1.4.
Oh, the significant figures?
Well, yeah.
Well, significant figures in your untransformed number can be the same, has to be the same as the number of decimal points in your pH or POH. So we got 2 decimals here. We can have 2 significant figures in that. You don't get it yet?
Well, you get 1.4 is not figure it out. Like,
Are you doing this one 10 to the minus 8.15? Is that what you're trying to do? Okay, we're out of time. Let's see. When we're trying to calculate the pH of an acid solution, if the acid is a strong solution, strong acid in aqueous solution, then all you need to know is the concentration of the acid as given in its molarity. Because it's going to completely dissociate. There's Katie. Once you know the concentration of the acid in solution, then you need to know, is it monoprotic, diprotic, triprotic? Because if you have a 1 molar solution of HCl, that's going to produce 1 molar hydrogen ions. Then you just use Sorensen's pH formula and calculate the pH. If we have 1 molar sulfuric acid, right, then you're going to have hydrogen ion concentration of 2 molar. Okay. The fly in the ointment is there's competition going on in every solution. And what you have to determine is who's the major player. In other words, look for major species in the solution first. The reason we're approaching it this way is because when you get to weak acids, this is essential. You've got to determine what the major species are. Otherwise, you get lost in the weeds and you start running down different rabbit holes for chemical reactions that don't matter. So you look for the major species and then you say, what possible reactions can occur? The question logically is, does the reaction go to completion, like with a strong acid, or is there an equilibrium that has to be determined? So if you have to do an equilibrium, an ice table, typically, then you would determine what the hydrogen ion concentration is at equilibrium. Then you can calculate the pH. All right. Examples. How about this aqueous solution of 2 times 10 to the minus third molar hydrogen chloride? What are the major species? Well, of course, you've got, come on. You've got hydrogen ions and chloride ions, and it's an aqueous solution, so there has to be water. That's obvious. So what's the pH? Since those are the only species, and water dissociates very little. Remember the Kw for water is 1 times 10 to the minus 14. Right? That's an insignificant contribution from water to the hydrogen ion concentration. So we can ignore it and focus on the hydrogen chloride dissociation. So the concentration of the hydrogen ions for this strong acid would be 2 times 10 to the minus third. Take the negative log of that, and you get a pH of 2.7. All right. What if you have a pH, what if you have a concentration of hydrogen chloride 1.5 times 10 to the minus 11? All right. We look at major species again. And if you calculate the pH then, hey, do you need copies of anything? Okay. Let's see if that's what I think it is. 1.5 times 10 to the minus 11. Let's just take the negative log of that and see what happens. Let's see. 1.5 exponent there. Log changes up. Yeah, 10.8. pH of 10.8. Actually, when you look at this number, what does that tell you about this solution? Is it acid or base? It's basic, right? Anything greater than 7 is basic. So when you have a concentration of your hydrogen ions that is less than 10 to the minus 7, you're going to end up with a basic pH calculation. All right. Okay. HNO3 in aqueous solution, nitric acid. So this reaction takes place immediately, and what we're given there in that slide is the true behavior of hydrogen nitrate in water. It reacts with water, transfers a proton to water, makes a hydronium ion, and leaves behind a nitrate ion. This reaction goes to completion because nitric acid is strong. right? So these are, I would call them ridiculous suppositions. Does nitrate react with water to produce hydrogen nitrate in solution and hydroxyls? No, it doesn't. Why? Because HNO3 is a strong acid. So what is the nature of its conjugate base? It would be a very weak conjugate base, NO3, which means it doesn't want hydrogen ions from anywhere. It's extremely weak. So that reaction is, I guess I could say, forbidden. It does not occur. Okay. So the reaction, we also have a competing reaction where water dissociates, right? Water molecules, this amphoteric nature of water occurs all the time. It's always there. But does it produce a major contributor to the hydrogen ion concentration? Typically, no. It doesn't. Because its equilibrium constant is 10 to the minus 14. And the equilibrium constant for nitric acid is negative. Actually, the equilibrium constant is not negative. It's very large, producing a negative pH. Come on, there we go. So if we want to calculate the pH of a solution of nitric acid at 1.5 times 10 to the minus 2 molar, notice that that is going to be completely dissociated, right? You have no hydrogen nitrate left. And that means that the concentration of hydrogen ions is much, much greater than 10 to the minus 7. That tells you, since we compare it to 10 to the minus 7, why? Because that's neutral, right? Kw for water is hydrogen ions times hydroxyl ions. That's equal to 1 times 10 to the minus 14, right? So each one of these has to be 10 to the minus 7 times 10 to the minus 7. So if it's much greater than 10 to the minus 7, right? 1, 2, 3, 4, in this case, 5 orders of magnitude stronger hydrogen ion concentration, then we can ignore that. We know it's going to be acidic, and we can just run the calculation. 1.5 times 10 to the minus 2, take the negative log, there's your pH, 1.82. Now, why does that pH have 2 decimal points? Remember that? It has 2 decimal points because the molar concentration of hydrogen ions has 2 significant figures. Okay, so that was a lesson in strong acid calculation. If you're dealing with a weak acid, you've got an equilibrium problem here because the acid only dissociates partially into hydrogen ions and conjugate base. So in this case, it's very important to list the major species. Then you choose the one that produces the hydrogen ions in excess of the other. In other words, which one controls the pH? Then you may have to write an equilibrium. Well, you write the reaction and then set up an ice table. Okay, those are the rules, but I think it'll make more sense if we actually do a sample or two. All right, so the rules for running an equilibrium calculation and the tricks that we used in equilibrium in chapter 13 still apply for chapter 14, 15 with acids and bases. So if we have this 0.8 molar aqueous solution, 0.8 molar aqueous solution of hydrocyanic acid, and we know, and we're given the Ka, right? of 6.2 times 10 to the minus 10. 6.2 times 10 to the minus 10. There we go. All right, what are the major species? What's going to happen when you put this in water? HCN is going to set up an equilibrium, and I'm using the abbreviated form here. Right? This is not where it reacts with water, but just know that it does. So those are the possibilities. And we have a little bit of each one of these in solution because it only partially dissociates, right? That tells you that it's a weak acid. So most of it is going to be here. That's a major species. These are minor species, so we don't consider them at present. We only consider this one and water. Okay. So, well, in the slide, we've given you the complete reaction. And water, of course, is just for comparison, 10 to the minus 14. So still, water is not a major contributor, right? Even though it's a weak acid, it's stronger than water, right? By 4 orders of magnitude. Actually, more than 4 orders of magnitude. So the reaction that controls the pH is that one. Oh, there we go. All right. That's the end of that lesson. We're not actually going to do it. We're going to go to hydrofluoric acid and use it for our example. So if we're going to calculate the pH of hydrofluoric acid, we have to say, what are the reactions that are in competition? Right? HF produces hydrogen ions and fluoride ions. And the Ka for HF is 10 to the minus 4. So even though it's a weak acid, we know it's stronger than water. So this is going to be the controlling reaction. Major species, of course, will be HF and water. And we compare the two, and that's the controlling reaction. All right. So if we set up our ice table, the initial concentration here is 1/2 molar, I believe. Yeah. And since this is the controlling reaction, we're going to say that those are 0. We know that this one is not. This one is 0 when we start. This one is a little above 0 because water contributes, but it's not a major contributor. So we can approximate it at 0. Okay, we're going to lose some of this one, right, in the equilibrium. And since it's 1 to 1 to 1, it's going to produce that. So 0.5 minus X, that's X, and that's X. Okay, what's the equilibrium expression? Let's see, do I have a slide on that one? Yeah. So the equilibrium expression for that one is the hydrogen ions, fluoride ions, divided by the undissociated acid. Okay, so we can insert these values with their unknowns. This is X times X over 0.5 minus X. Okay, and that's equal to this value. All right. Notice what we've got here. I mean, if we follow through with this calculation, we've got a quadratic on our hands. But since this value is so small, the production of this X compared to that 0.5 is very, very small. So what we're going to do is approximate this as X squared over 0.5 is equal to 7.2 times 10 to the minus 4. And solve for x. We just say 0.5 times this one, square root, and you got your answer. Let me see if I can do that. 7.2 exponent -4, 0.5 times that, and then take the square root of it. So I get that's x. 1.9 times 10 to the minus 2. Well, they carried it out more decimal points than I did. You should only need 2. And then calculate the pH. Since this is the hydrogen ion concentration, we just take the negative log of that. And since we've got 2 decimal points here, pH can, 2 significant figures, we can have 2 decimal points. Okay. This is the long way around. This is the long way, the equilibrium way. When we get to a discussion of buffers, I'm going to give you a shortcut. But you got to learn it this way to understand why the shortcut works. Okay. So this is a calculation of the difference, all right, to justify this approximation here. If we plug that 1.897 times 10 minus 2 into this position right here, leave those alone and recalculate the, let's see. No, we need to put the whole thing in there. We need to put the X value in here, here, and here, calculate what Ka would be, then compare that Ka to this one. Is it within 5%? That's what all that calculation is about. And it turns out that we were only off by 3.9%. So our approximation was valid. I'm not going to go through that mess. That's why I put it on the slide, so we wouldn't waste time writing it on the board. All right, next. Okay, there's another concept that we need to introduce. Percent dissociation or percent ionization. Actually, percent ionization is a better term because especially weak acids have strong covalent bonds between the hydrogen ion and the conjugate base. So they have to ionize. Dissociation is more properly used for bases, like sodium hydroxide. It's a sodium ion and a hydroxide ion with an ionic bond, so it just simply dissociates into its ions. This percent ionization is related to, but a slightly different concept for acids. Percent dissociation and the relationship of the percent dissociation to concentration is inverse. So as the concentration goes down, percent ionization goes up. All right. Percent dissociation, well, I didn't put the complete definition here. The amount ionized over the total amount. And this is in molarity. Those are concentration values. Times 100. Here we go. All right. So the next couple of slides, we're going to prove this relationship. In other words, if we start off with 8 molar formic acid, which is a weak acid, CHO2. And we're given that the percent ionization is 0.47%. So it is definitely a weak acid. What's the Ka value? All right, we set up the equation, the formic acid, oops, left out an H. H2, there we go. And this is an equilibrium with hydrogen ions and the formate ion. Okay, if we set up our chart there, we have 8 molar to begin with, 0 here and 0 here. This is going to be, since it's, well, we don't know what the K is. We have to calculate it. So maybe I'll put it the whole thing and explain it, at least for this first one. Right, 8 molar, that's 0, that's 0. So we're going to lose one of these, and we're going to get one each of those. But what is this? We can actually calculate what that is, right? Because we're told it's 0.47% dissociated. So what's the decimal equivalent of 0.47%? Move the decimal 2 to the left, 0.0047. That's the decimal equivalent of percent. That's why we multiplied 0.0047. The amount that's dissociated from here is the amount that's lost. So we can say 8, let me do better than that. 8 times 0.0047. That's how much is lost. And the same amount is gained over here. Okay. So if we do that calculation, subtract it from 8, we end up with 7.9624. And we get over here 3.76 times 10 to the minus 2. And these are all molar. Okay, now we've got those equilibrium values, we can calculate K. All right, I think that's what we do on the next slide. There we go. So our K is 1.78 times 10 to the minus 4. Okay. Now that's constant. Right. We're not changing the temperature. So that K is the constant for any concentration that we use, any concentration we start with. So we're going to start with a decreased concentration and see what happens and calculate the percent ionization from that. Right. Oh, did it tell us to calculate the pH? No, it didn't. We're just doing it for fun. Okay, so the pH is 1.42. We just take this value, negative log of the hydrogen ion concentration, you get 1.42 is the pH of an 8 molar solution. It's pretty, that's a low pH. That's about stomach acid. Okay, what happens if we change the concentration to 4? We go down, percent ionization should go up. But the K is going to be the same, but the percent ionization is going to increase. All right. Okay, let's see. Oh, I thought we were going to actually, okay, we're going to do it theoretically first. So I'm going to leave that stuff there. And this is 8 molar is 0.47% ionized. So I can erase this. Okay. If we take a generic acid, HA, a weak acid, and we write this equation for it, then we can calculate the Ka, right? Right, the hydrogen ions conjugate base divided by the undissociated acid. All right. So our the HA is going to be the initial concentration of the acid minus how much we lost. Right. That's what the X means. And that's an approximately, it's approximately the same as the initial concentration if it's a very, very weak acid. Right. That's our approximation that we used before. Let's see. Oh, somebody just dropped out and come back. Okay, that's fine. And the hydrogen ion concentration and the conjugate base are going to be equal. Right? So we can write the Ka as X squared over HA initial. That's going to be probably, for most weak acids, that's going to be within 5%. So that's our first approximation for Ka. So what happens if water is added so that the concentration, the actual concentration, not the initial, with that little zero, that's the initial. The actual concentration becomes 1/10 as strong. So we're going to dilute 1 part of our original acid with 9 parts of water, make it 1/10 as strong. All right. So let's recalculate. Okay. We've got a new concentration for the conjugate base, and the hydrogen ions are equal to X divided by 10. So we substitute those in as the new concentration of HA. Now that we've stressed the system by adding water and reducing the concentrations, which way will the reaction proceed? Well, let's see. If it was at equilibrium here, what did we do? We made this weaker, right? We reduced the concentration of hydrogen ions. What does Le Chatelier say is going to happen? No idea. If we reduce that concentration, it's going to move this way, isn't it? That will increase its dissociation. So on a qualitative basis, Le Chatelier says, yeah, that's right. That's what's going to happen. We're going to increase the ionization by decreasing the concentration. But here's the actual calculation. All right. If we decrease everything by a factor of 10, right? We divide X by 10, we divide the initial concentration of the acid by 10, then we can calculate the Q before equilibrium. And the Q then is going to be 1/10 of our original value for K. Right? So if the Q is less than K, right? What happens if Q is less than K? Which direction are we going to move? If Q is less than K, you don't have enough here, right, in the numerator. So it's going that way. So that's 2 ways to justify the movement. So the percent dissociation now increases. We have a new value for this one, but now we also have an increased value for these two. So the percent ionization increases. Now the overall concentration is less, right, because we diluted it. But the percent, which is an intensive property, increases. All right, so now we're going to take this 4 molar formic acid, and I think we're going to see the shift to the right. We're actually going to do the calculation. Right? Now that we know what K is, right, we can set our expression equal to K, and we just substitute in here different values. Right? This is going to be 4 molar now. Right? And this is going to be minus X, and these are going to be plus X. And we get 4 minus X, and then X, and then X. And the expression becomes now X squared divided by 4, because we let this one, based upon the small value of the K, we let this one equal 0. And we find out that X is 2.665 times 10 minus 2. Molar. Okay. Now, what does that mean? That means if we subtract that value from 4, that gives us what's left over. Actually, this tells us how much was dissociated. So we take this one, divide by that one times 100. And that will give us the percent ionization. Come on. There we go. 0.67% ionization now. So at 4, this is for 8 molar. For 4 molar, we have 0.67% ionization. So the ionization has increased. Percent ionization increased. Right. So we went Le Chatelier, we went calculate Q, then we actually quantitatively calculated the value. And all 3 ways prove the point. Decrease the concentration of a weak acid, you increase its percent ionization. All right, so if we take that value and do the log transform, the pH now did what? The pH actually went up, right? What was it? 1.2 before, wasn't it? .42. Okay, so this is pH 1.42. No, I think the pH went, it got smaller. Okay, the pH of this one now is 1.57. Okay, so it's more basic. The percent ionization went up, but since we diluted it so much, even then the pH became more basic. Right? It's not as acid as it was by about 1/10 of a value, 1/10 of a pH unit. All right, let's talk about bases now. We defined our base already. And according to Bronsted and Lowry, a base is a proton acceptor. But in most cases, bases will have a hydroxyl in their makeup. Right? Just like lithium, sodium, potassium, calcium hydroxide, all those are strong bases, right? In the chemical sense. Now, lithium, sodium, potassium, those are all alkali metals, hydroxides. So they will completely dissociate, right? They're definitely strong bases in our intuitive sense of what a strong base is. But calcium hydroxide is a strong base. It's just not as soluble. So by definition, when calcium hydroxide goes into solution, it produces calcium ions and hydroxide ions only. There's no calcium hydroxide drifting around in that solution. It's a strong base in the chemical sense, although it's not very soluble. Right, so there's your paradox. All right, so we learned also that POH, we can calculate POH if we know the hydroxyl ion concentration, and we can calculate pH from that if we subtract it from 14. Right, we learned that one last week. All right, so what's the pH of a solution of sodium hydroxide is 10 to the minus 3 molar. Just calculate the POH, subtract it from 14, and you get pH 11. Right, and that intuitively says, yeah, that's greater than 7, so it's basic. Right, makes sense. How about 10 to the minus 3 solution of calcium hydroxide, right? If we know that it's 10 to the minus 3 molar calcium hydroxide in solution, then we're told that's part of it that is soluble, right? We may have put just enough to make that soluble, right? If you don't put any excess, but you could put excess maybe, and that's what you end up with. We have 2 hydroxyls in this case. So 10 to the minus 3rd molar is 2 times 10 to the minus 3rd hydroxyl. So that's the one that we calculate the pOH, 2 times 10 to the minus 3rd. And subtract that from 14. So our pH now is 11.3. Let's see, what was the concentration of the first one? Same thing, right? It was only pH 11. But if we have the same concentration of calcium hydroxide, we get a pH of 2. Excuse me, a pH of 11.3. So it's slightly more basic. Okay. I think I went through the calculation of a KB last week, didn't I? We'll go over it again. So if you put, how would you get the cyanide ion in solution without the hydrocyanic acid? You use the salt. Well, I haven't defined salt yet. So you use, say, potassium cyanide in aqueous solution. And that produces, all potassium salts are soluble. So that produces the cyanide ion in solution. Now, what's it going to do when it encounters water? Well, it comes from a very, very weak base, right? I think it was 10 to the minus 10 K. A very weak base, that means, very weak acid. So this base is going to be very strong. That means what you're going to get is Cn minus is going to react with water and take a proton from it, make the hydrocyanic acid, and leave behind the hydroxyls. So when you put the conjugate base of a weak acid in solution, you get a basic solution. And then the Kb calculated from this, right? That's a liquid, so it doesn't count. So the Kb then is calculated based upon the conjugate acid of the base, the hydroxyl ion concentration, divided by the cyanide ion. So that's your Kb. All right, let's see. That's repetitive. We'll skip that one. This is supposed to, that little box is supposed to be a double arrow. I think when we upgraded our Microsoft Office, it didn't have the right font. So it substituted that box in there. That's a double barbed arrow. All right, so ammonia plus water makes ammonium ion and hydroxyl ion with a Kb of 1.8 times 10 to the minus 5. So what's the pH of a 2 molar solution of ammonia? All right, if we set up the Kb, now this Kb is drawn from the ice table. If you say ammonia plus water yields ammonium plus hydroxyl, then the initial concentration of ammonia is 2 molar. And the initial concentration here is 0 and 0. You're going to lose one of these. You're going to end up with one of those and one of those. So this has X, this has X, and this is 2 minus X. So when we set up our Kb expression, it's going to be X squared, right? Kb B equals X squared in the numerator, right? X times X. And in the denominator, it's 2 minus X. But we're going to approximate, right? Since the K is 10 to the minus 5, we can approximate that as x squared over 2. And this is equal to 1.8 times 10 to the minus 5. Well, that's almost the same as acetic acid, isn't it? Numerically, right? It's a different calculation though. Acetic acid is Ka. Okay. So if we calculate the x now from that, we get, there it is, 6 times 10 to the minus 3. 6 times 10 to the minus 3 molar. That's hydroxide ion concentration. So if we do the pOH, 2.22, and subtract that from 14, our pH is 11.78. Right? The reason I went through all that ice table is just to bring you along and show you that where that expression came from. Right? That we just threw it up there on the slide, but it came from the ice table. All right. How about polyprotic acids? I mentioned that a little earlier. Monoprotic has 1 proton available to ionize off of an acid. Diprotic has 2, triprotic has 3. Anything 2 or greater is called polyprotic. So what we have learned is that when we have something, we'll use a real world example. Say phosphoric acid in aqueous solution. How is it going to go into equilibrium? When a proton dissociates from an acid, and there are more than one possible, like a polyprotic, it does so 1 proton at a time. There's an equilibrium set up with the 1 proton dissociation. So that would leave us 2 of these, PO4 minus. That one will have a K, a Ka1. Okay. Then in solution, that H2 PO4 minus can set up an equilibrium with another proton dissociation, PO4 2 minus. Then we can take that last one, and it sets up an equilibrium like this, PO4 3 minus. And each one of these has its own K value. All right. What we've learned is that this K is greater than the second dissociation K is greater than the third dissociation K. And usually the difference between the two is huge. Most of the time it's very large. And what that means is the pH of polyprotic acids will be determined by the dissociation of the first one. The Ka1 is the determining K for the pH of a polyprotic acid solution. So phosphoric acid is weak acid all the way. So all of these are less than 1. Right? But sulfuric acid is a diprotic acid, and its first proton dissociation is complete. That's the strong proton from sulfuric acid. The second proton from sulfuric acid is weak. And that's typical. If you have a polyprotic acid that is labeled strong, it's only strong for the first proton. All right. So here we have our phosphoric acid, and there you're given the Ks. Right? The first one is 10 to the minus 3, 10.5 times 10 to the minus 3. The second one is 10 to the minus 8. Right? 5 orders of magnitude weaker. And then 4.8 times 10 to the minus 13. 5 orders of magnitude difference here and here. So these two are insignificant for determining the pH. Now, if you need to determine what is that concentration in solution, then you've got to go step by step. All right, here's the first dissociation. Right there. That's what it would look like. That one times that one divided by this one. And the pH of a 1 molar solution, we calculate X, which would be the hydrogen ion concentration. Here we go, is 0.0866. Now, does it obey the 5% rule? So we calculate the K based upon that hydrogen ion concentration that we calculated. And we find that it's not. It does not obey the 5% rule. So what do? Well, you have two choices. You can either set up the proper equation and do the quadratic solution, or you can take that value, put it back in the expression, the expression on the previous page, 0.0866, let's back up. Put 0.0866 down here, right here next to this 1, and then calculate the X again. Now let me see, what did we choose to do for this one? Since it failed. Okay, successive approximation, we're going to do it that way. Substitute 0.0866 in the X of the denominator, then recalculate the X. There you go. Once we calculate that X, we find that it is 8.2728 times 10 to the minus 2. Now we recalculate the K value with that new value of X. And we find out that it's much less than 1%. So successive approximations works great. Usually within one approximation, you can get the right answer. Sometimes it takes 2 or 3, depending on your reaction. But I think this is a whole lot easier than trying to do the quadratic. Now you can do the quadratic, that's no problem. As long as you've got an x squared polynomial, you can do the quadratic calculation, just, I mean, if you feel comfortable with it. But this approximation method is also valuable, and successive approximations works no matter how many powers of X you have. You can have a cubic or a quartic or a quintic equation. It works for any one of them. All right. So then we calculate the pH at 1.08. And the reason we do it with only the first is because it is the controlling reaction. 5 orders of magnitude difference. This second dissociation contributes nothing to the hydrogen ion concentration. Okay. In this example, we are going to find out what is the concentration of phosphate. And to do that, we need all 3 of these equilibrium values, these K values. All right. So if we start off with 1, we've already determined that the equilibrium concentration of hydrogen ions and dihydrogen phosphate ion is 8.28 times 10 to the minus 2. That's our starting place, right? So then we subtract X from one side, add it to the other. We get the values at equilibrium there. And then we take those values there. And we find that X didn't change. Right? X is the same, right? X is the same because of that value so small. So the value of hydrogen ions we calculated originally, we can carry it through all 3 calculations. We can go to the last one. Here we go. Now at the very end, we know that the hydrogen ion concentration is this value. And it didn't change, right? Because we calculated the hydrogen ion concentration for the last equilibrium and added in there, and it's so small it doesn't even matter. So now we get down to the bottom here. The hydrogen ion concentration at the end is still 8.28 times 10 to the minus 2. And that's what we started up here, because that one's so small and that one's so small. it didn't change. So we know what this is. We did calculate the HPO4 2 minus concentration is 6.2 times 10 to the minus 8. All right, let's go back so that you understand what we did here. Okay. Yeah, X. We calculated X at HPO4 2 minus. Okay. And then we added, let's see, why did we add? Oh, that's the X. We added the X. Right. Well, that's the hydrogen ions. I'm trying to find out where we got this value, 6.2 times 10 minus. Oh, that's the K. That's the K from the original. Okay. Then we calculate the K for the final one. Actually, we calculate the phosphate concentration from this. And it's very, very small, extremely small. 10 to the minus 19th molar. Now, when you do a titration with phosphoric acid, if you use a strong base, the strong base is first it's going to take this hydrogen ion, then it's going to take this one, then it's going to take that last one. And when it takes that last one, you're down to this position. And that's the titration that gives you the overall concentration of your phosphoric acid. All right. Now, define what a salt is in chemical terms, right? We had a difference of opinion with popular media on what a strong acid and a strong weak acid was. We dispelled that. A salt in popular media is sodium chloride. And potassium chloride is light salt. Those names are based upon what they do. In chemical terms, a salt is based upon the reaction of an acid and a base to produce water, right? One hydrogen, one hydroxyl makes water. And then the cation plus the anion. This is the salt. In chemical terms, that's the salt. This, of course, is an acid. This is a base. And this is obviously water. Okay. The vast majority of acid-base reactions will give you water plus a salt in chemical terms. Now, can we predict when we add an acid and a base together, can we predict the outcome? Is it going to be acidic or basic? If we dissolve a salt, say we take the salt here and put it in water, what's the pH of the solution? Well, we can't say exactly unless we know what the Ka and Kb's are, but we can roughly estimate what the pH is going to be. I mean, it's going to be acid or base, or is it going to be neutral? We can say for a salt that's made from a strong acid and a strong base, right? If both of these are strong, when you make the salt and you put the salt in solution, then you end up with approximate pH is going to be neutral. Right? Nobody wins. That will produce a neutral solution. Let's see. Okay. If we form it from let's see, in this case, we're forming from strong base and a weak acid. If we put the salt of this combination in solution, we get a basic solution. Okay. And if we flip that and say we form a salt from a strong acid and a weak base, then we get an acidic solution. Okay. Now, the one that we're not too sure about is weak and weak. Weak and weak. In this case, we have to compare the Ka and the Kb for each one. If the Ka of the acid that goes into the salt is greater than the Kb for the base that goes into the salt, then we get an acidic solution. If the Kb is in excess, we get a basic solution. All right. So we can make a prediction, but we have to have that quantitative data. So let's see. I think we learned how to do this before, didn't we? If we have a Ka, how do you calculate the Kb? Remember that? Didn't I do that for you? If Ka equals, excuse me, Kw equals Ka times Kb. So if you know the Ka and you want to find the Kb, then you say the Kb is equal to the Kw divided by the Ka. And you can swap these two and do the other calculation if you want. So that's 1 times 10 to the minus 14 divided by Ka gives you the Kb for the conjugate base. So if we had, let's see, acetic acid, say, the Ka for acetic acid is 1.8 times 10 to the minus 5. So the Kb is going to be, let's see if I can do that. Is going to be 5.6 times 10 to the minus 10. Okay. But what does that mean? That means the Kb for what? For the C2H3O2 conjugate base of acetic acid. That's what we're saying. So when you put this in solution and react it with water, right, you set up an equilibrium with the acid producing the hydroxyls. That's what this is based upon. And we could do the same thing for the cyanide ion also. All right. Come on. There we go. All right. All right. I'm starting to run out of time. The point of these next slides is to show 2 different ways to put these 1 molar solutions in order of lowest to highest pH. We can do it qualitatively. If we say, all right, what would be the lowest pH? It would be the strongest acid in that group, correct? And what's the strongest acid in that group? No idea. All acids formed from halogens are strong except for this one. So that's strong. This is stronger. That's even stronger. So hydroiodic acid is the strongest. Hydrobromic acid is a little weaker, but it's still strong. Hydrochloric acid is strong also. All right, so hydrobromic acid would be the strongest in order from lowest to highest pH. So the lowest pH would be the strongest acid. Right? So as far as, well, let's say if we do it in terms of pH, that's the lowest pH right there. Okay, what would be the highest pH? It would be a strong base, wouldn't it? What's the strongest base in there? What did I do? Oh, I left my drink. I'll give you time to think about that. I'll go get my drink. Take a wild guess. Which is the strongest base? We just went over that. Sodium hydroxide would have the highest pH. All 1 molar solutions. Okay. Which one's neutral? Well, I gave it to you. The one that's formed from a strong acid and a strong base would be neutral. So right in the middle of this whole mess is sodium chloride, sodium hydroxide, hydrochloric acid. Okay. Okay, so we got 3 of them out of the way. That one's neutral. Let's see. Strong base, there you go. Ammonia is not as strong as this one, but it's pretty strong by comparison. How about the other side? All right, weak acids. We have, let's see. Oh, we've got a strong base and a weak acid, sodium cyanide. So that's going to be basic. It's going to be on that end. And then, yeah, we've got the acids. HF is a weak acid. So it's probably going to go right there. Right, this is stronger than HF. Okay. Now we have hydrocyanic acid and ammonium chloride. Ammonium chloride is formed from a weak base and a strong acid, so it's going to be acidic. And hydrocyanic acid is going to be acidic, but we don't know which is which. I mean, which comes first? We're going to say since hydrocyanic acid already has the hydrogen ion, it's probably going to be stronger than, what did I say the next one? Ammonium chloride. There. So that should be the order. HF, HCN, ammonium chloride, sodium chloride, CN. Okay. That's qualitative assessment. We can do a quantitative assessment by comparing the KAs and the KBs. Right? So here we have a list of the KAs and the KBs for each one of these acids and bases, and that puts them in the correct order quantitatively. Right? HBr is a strong acid. It essentially doesn't have a Ka. HF is 10 to the minus 4, HCN and has its value. And ammonium chloride, Ka, is calculated at just slightly smaller. And then we have the neutral, and then the KBs take you and finish the job. So that's the quantitative approach. All right. Why are we saying consider this? Doesn't ask a question yet. What are the major species for sodium fluoride in solution? Well, all alkali metal salts are soluble, completely soluble. All right. So sodium fluoride is going to go into solution. It's going to be sodium ions, fluoride ions, and water are the major species. All right. So why isn't sodium fluoride considered a major species? For the same reason I just told you. It completely dissociates, right? It's not even in the solution. So how about dominant reactions? Well, major species, fluoride could react with water, right? It's not going to react with sodium. Right. Let's see, where is it? There it is. It's not going to react with sodium because it's already completely dissolved, right? It's completely soluble, so it's not going to go backwards, right? And then water, you got that reaction. You got fluoride ions reacting with water. You've got, does sodium react with water to make sodium hydroxide? I don't think so. It's a spectator. All right, so we can throw those out and keep the top two. So which one of these controls the pH? That one or that one? Look at the Ks. All right. What's the Kb? We take the Ka for hydrogen fluoride, calculate the Kb, right? Because that's the Kb. Fluoride plus water produces the hydroxides. We have to use a Kb in that case. So the Kb for this one is Kw minus Ka, 1.39 times 10 to the minus 11. And then water is 10 to the minus 14, right? So the Kb for fluoride is 1,000 times larger than the Kw. So the fluoride reaction is the controlling reaction. We can do the same type of reasoning for sodium cyanide, right? Major species here, sodium cyanide ion and water, right? And we can throw out the ridiculous ones and then make the comparison between the cyanide Kb and water. We find that the cyanide is the controlling reaction. Then we can set up our equilibrium, our ice table, using that equation. And that will calculate the X, which is hydroxyl ion concentration. Calculate the pOH, subtract it from 14, and now we know our pH is 11.54. Okay. So what determines the acidity in a binary acid or a base? There are two things. How polar is the bond? Right? And we're talking about acids here. If we're talking about polarity, it has to be acids because they're covalent bonds. So the polarity of an acid bond determines its strength. Also, how strong is the bond? Right? We can say, we can use polarity in some cases, in other cases we need the bond strength. So a weaker bond makes a stronger acid. And for polarity, the more polar the bond, the stronger the acid. So here we have a comparison of bond strengths. Right? HF bond strength is 565 kilojoules per mole. Right? It takes a lot of energy to break that bond. It takes a little bit less energy to break the bond between hydrogen and chloride, and even less for bromide and iodide. So as a consequence, hydrochloric acid is strong, hydrofluoric acid is weak. That's based upon bond strength. How about oxyacids? An oxyacid is one in which the hydrogen ion that you're going to dissociate is attached to an oxygen, and then you have something else out here. I don't know. They say X, I'm going to say R. Because R could have something else attached to it. It could be another hydrogen, it could be a double bonded oxygen, it could be anything else. But this is an oxyacid where that hydrogen is attached to an oxygen and then attached to the carbon chain or whatever else. So for a given series, the acid strength increases as the number of oxygens increase. Here's a perfect example. Remember when we were studying nomenclature, right? And I started with the chlorate ion, right? That's chlorate. If we take away an oxygen, we get chloride. And if we take away another oxygen, we get hypochlorite. If we add an oxygen, we get perchlorate. Okay. Notice the increase in number of oxygens here. Well, if we make an acid out of each one of these, and of course that will cancel the negative charge, and the name will change. Instead of ATE, and that one, we get perchloric acid. We get chloric acid. We get chlorous acid. And we get hypochlorous acid. Now, how do the strengths of these acids compare? The strength increases this way. The more oxygens you have, the stronger the acid. So perchloric acid is the strongest in that series because it has more oxygens. Now, why? Why does it do that? Because the more oxygens you have attached to that chlorine, oxygen is electronegative, chlorine is electronegative, and they're drawing electron density away from the bond here. Right? And they're weakening the bond by drawing, by making it more and more polar. So this is slightly polar. Let's see, this way. This is a little more polar. This is a little more polar. And this is extremely polar. That weakens the bond with hydrogen and makes it more acidic. And there are the numbers to prove it. Okay. How about electronegativities? Right. Well, if we compare, let's see, the example they're using is this one. So if we take these out of the picture, and instead we put this one. Actually, that's not the right way to write it. It should be CLO like that, and BRO like that. I think. Yeah. And IO. Okay. Am I out of time? Oh, you need to take a break. Okay. So what's the electronegativity? Well, the electronegativity increases this way. Electronegativity increases that way, and so does the strength of the acid. Increases that direction. And for a similar reason to my previous argument, with more oxygens, if you increase the electronegativity, here of this iodine versus that bromine versus that chlorine, it's drawing electron density away from that bond and weakening the bond. So this is the stronger acid because that hydrogen leaves with less energy required. Okay, HOF is not in that series because it decomposes, so we don't even consider it. All right. If we, previously, we put salts in solution to determine what was the product, right? Was it acidic solution, neutral, or basic? Now, if we take oxides of various oxide compounds, let's say, and put them in solution, we can divide them into two categories. One are the acidic oxides. The acidic oxides are formed from nonmetals. These are nonmetal oxides. When you put them in solution, they react with water and produce an acidic solution. They're often called acid anhydrides. Because when you put them in solution, say SO2, let's use SO2 as an example. It's a gas, but if you bubble it in water, what reaction do you get? You get H2SO3, right? 3 oxygens, 1 sulfur, 2 hydrogens, and there's your acid. So when sulfur dioxide is blown out of coal-fired power plants, not so much anymore, but it used to be, it combines with rainwater, and that's where you get acid rain. Well, nitrogen dioxide also does that. Carbon dioxide, of course, carbon dioxide is an acid oxide, acidic oxide, right? Carbon dioxide plus water produces carbonic acid. Whether it's coming out of the sky when the rain falls, or whether it's coming out of your pop bottle, it's still carbonic acid. So acidic oxides in solution are formed from non-metal oxides. Basic oxides, you probably can guess, are formed from metal oxides. It's on the next slide. Yeah. Such as calcium oxide. What happens when calcium oxide combines with water? What does it produce? It produces calcium hydroxide, which is a base. So metal oxides dissolved in water produce basic solutions. Non-metals oxides produce acidic solutions. All right. I'm going to introduce this topic. It won't be much use to you unless you go into organic chemistry, but you need to at least hear about it. We had Arrhenius definition of an acid and base. We had Bronsted and Lowry's definition. Then we have Lewis definition. The Bronsted-Lowry expands upon Arrhenius and includes Arrhenius in its definition. Lewis expands on Bronsted-Lowry and includes everything that Bronsted-Lowry and Arrhenius said about acids and bases, but goes even further. Because now, instead of focusing on the hydrogen ions, we focus on the electrons. A Lewis base is an electron donor. Right? So if we had a Bronsted-Lowry base, like, let's use ammonia. Right? So we know that if we write ammonia in its Lewis structure, it has a pair of electrons there, like that. Okay? Now, if it reacts with water, right? And water, let's write it in its Lewis structure. Water, right, will produce NH4 plus. Lone pair's gone. Where did it go? It was donated to a hydrogen. One of these hydrogens, right? One of those hydrogens got that pair. Okay. So this is the base, the Lewis base. It donated these electrons to that hydrogen and formed the bond. And it left a pair behind. This is the electron pair acceptor. So when we break that bond, those two electrons went to this oxygen. So this is a Lewis base. Protons, electron donors, and this is a Lewis acid. Electron pair acceptor. And there's another example there. I'm not going to go into that. All right. The Lewis model is especially useful for non-aqueous environments. You can speak of non-aqueous reactions in terms of acids and bases if you invoke the Lewis definition. And that's why it's very useful for organic chemistry, because many of the reactions in organic chemistry occur in non-aqueous solutions. And they do so because you don't want water messing with your reaction. Right? So you exclude it, but you still have to talk about it in terms of acid base. Okay, so this is just a summary of what you do when you have an acid base problem.